Hi folks, welcome to part 2 of the first Unit 5 lesson. Okay, so remember we left off, we defined these new quantities called vectors, which include both a numerical value and a direction, and to distinguish them from quantities that are just represented by numbers, we called those scalar quantities. Okay. So since we're defining these new mathematical objects, there's certain relationships that we're hoping to find. And the first thing is, well, what does it mean for two vectors to be equal? Now, we pretty much answered this question in the first video. Okay, so if I take this as a vector, we said that a vector was defined by its magnitude, which is represented by the length of this arrow, in its direction. In other words, the direction that the arrow is pointing. So essentially, if I take any other vector which has the exact same length and points in the same direction, that should be equal. But what's nice about this is it means that the location of the actual vector is unimportant. Okay? So this vector here is also equal to the green vector, and this vector here is equal to the green vector, and that vector there is equal to the green vector. Why? Because it has the same length and points in the same direction. Okay, so that is one of the most important things to take out of this, is that the placement of the vector is of no importance. It's all about magnitude, length, and direction where it's pointing. Okay, so what about an opposite vector? What do we mean by that? Well, what we mean is just the same magnitude but in the other direction. So in other words, just pointing in the exact opposite direction. And of course, we can move this vector anywhere. So this is what we mean by opposite vectors. Now, you might say, why is it so important to know about opposite vectors? Well, one example that, even though there's a physics example, I think most people have heard that if I have, say, Broccoli Bear standing on a floor, well, Broccoli Bear is applying a force onto the floor. And why isn't Broccoli Bear, sort of sinking down to the center of the earth? Well, that's because the floor is applying an equal and opposite force onto him. Okay, so this is one example of why we need an opposite vector, something that represents having the same value, the same numerical value, but opposite direction. Okay. Then we have something called parallel vectors. Well, parallel vectors, it would make sense that even if the magnitude is not the same, but they're in the same direction, that these two vectors would be parallel. Okay, if you think of parallel lines. But we can take it even further. It doesn't actually necessarily have to be in the same direction. It could even be in the opposite direction. Okay, so one way to think about it is that parallel vectors are any vectors that can be drawn along the same line. So remember, this vector here can be moved wherever we want. So we can put it there, and we can put this there. And we see that all three vectors can be drawn along the same line. So same or opposite direction. All right, so let's go back to our sheet, and let's define these here. Okay, so what does it mean for two vectors to be equal? They have to have the same magnitude, and they have to have the same direction. All right, so this is where, good idea to remind ourselves that the location of the vector is irrelevant. The location of the vector is irrelevant. Okay, so these two vectors, even though they're not in the exact same position, represent, you have to imagine they're the same length, maybe a little off here, that as long as they're pointing in the same direction and they have the same length, they're equal vectors. Okay, opposite vectors would have the same magnitude, but opposite directions. Okay, so here, this vector and that vector are opposite, same magnitude, opposite directions, and parallel vectors are any vectors that have the same or opposite directions. All right, so here this vector is parallel to that vector, is parallel to this vector, is parallel to that vector, as long as the direction are same or opposite. All right, so now it stands to reason that, especially when we're talking about these parallel vectors, well, how are we going to represent a vector that has the same direction but not the same magnitude? Okay, so we're also going to talk a little later on about, in fact, probably in this little section here, I'm also going to talk about how we might represent opposite vectors. Okay, so let's go back to our use of cardinal points to represent a vector, and then we'll also use arrows again. So let's say I have a vector v. Okay, now notice here, a vector v needs to be distinguished from a scalar. So when I, in this last example, talked about this vector v, well, v, is a letter which normally represents, which is a variable which represents some number. So we can't actually be using v on its own to represent a vector, since we've already used letters to represent scalar quantities, in other words, numerical values. So using this idea of an arrow, as we put a little arrow on top to represent a vector. Now, in the old days, it was pretty hard with typesetting to have an arrow on top. So in some older textbooks, you might actually just see a bolded variable to represent a vector, but most textbooks now will have the arrow above. Okay, so let's say this vector is the vector 20 kilometers per hour heading north. Okay, so let's say, so in this case here, our vector would be a velocity. Okay, so the numerical value, the speed is 20 kilometers an hour, and it's telling us heading us north. So let's say I want to talk about a vector which is 3 times the magnitude, so in other words, 3 times as long, okay, but still in the same direction. Well, we notice here what hasn't changed is the direction. The only thing that's changed is the numerical value. Okay, the numerical value has been multiplied by, not 5, of course, but by 3. Okay, so what we do is we just represent this, okay, as 3 times v. Okay, so this represents a new vector quantity, okay, where the direction hasn't changed. The only thing we've done is we've multiplied the numerical component. Okay, now this is going to bring us to our next question, which is this idea of operating with vectors. Okay, we've defined this new mathematical object, and when you define a mathematical object, so say numbers, what can you do with numbers? You can operate on them, add, subtract, multiply, divide. We then saw that with mathematical objects that were functions, that we could also operate with functions. We could add functions, we could multiply functions, we can take inverses of functions, all right? We can square functions. So it stands to reason that as we define these vector quantities, there might be some operations we can perform on them. All right, so now let's say we want a vector, in this case here, whose magnitude is half as large, okay, and in the opposite direction. So in other words, I want to describe the vector that's 10 kilometers per hour in the south direction, okay. Well, we already know how to handle cutting the magnitude in half. Well, I would just multiply my vector v by 1/2. Okay, except when we did this multiplication, it was assumed that the direction was staying the same. So we need a way to describe this direction being opposite to the original one of north. And I don't think it's going to be too surprising that we use our one-dimensional motion as inspiration. Okay, so what did we use for opposite direction when we were talking in one dimension? Well, we just used the sign. So here, this is going to represent moving in an opposite direction. Okay, so this represents that it's half the magnitude. The 1/2, so in other words, the absolute value of this number. of that coefficient, okay? And the negative itself represents being in the opposite direction. All right, so if now we're starting to take these vectors and starting to operate with them, well, we need to study this here, okay? And this type of multiplication, okay, notice I say this type of multiplication, so I seem to be indicating that there might be other types of multiplications. We see that we have a vector that's being multiplied by a number, in other words, by a scalar quantity. And so this is why we call this type of multiplication scalar multiplication. In other words, multiplying a numerical value times a vector quantity. Okay, so this is where we're going to move on to the next page. Okay, and this is going to be our first go at having operations on vectors. Okay, so I want to represent this in the most general way. So if I'm going to multiply this by a scalar, I'm going to represent that by some unknown, and I'll call that k. Okay, so what does this represent? Okay, well, it represents a vector that's going to be, well, either in the same or opposite direction, because as we saw before, if I multiply this by a positive number, it's going to be in the same direction, whereas if I multiply it by a negative number, it's going to be in the opposite direction. So those are the only two options, same or opposite direction. But we know that this is going to have an effect on the magnitude of this vector. Okay, so question is, I have to be careful because magnitude, if you think of a vector as being an arrow, the magnitude, well, is just a positive quantity because it's representing a length. Okay, but this number here could be negative. So what can I use to get around that? Well, of course, I'm going to use the idea of absolute value. Okay, so kv is a vector. Okay, so first and foremost, when I multiply a vector by a scalar, I get another vector. Okay, and it's going to be k times the length, or k times the magnitude of the original vector. But to ensure that I'm working with a positive quantity, I'm going to say it's the absolute value of k times the magnitude of vector v. Okay, so now I've described the magnitude of this new vector. I need to describe the direction. So anytime I'm talking about a vector, I need to be talking about both. Okay, and we're going to say, and in the same direction, if k is positive, and in the opposite direction, if k is negative. Okay, so first of all, we realize that kv is either in the same or opposite direction as the vector v. So how did we describe vectors that were in the same or opposite direction? Well, we called them parallel. So therefore, we can say kv is parallel to the original vector v. Okay, you're always staying in the same or opposite direction, so along the same line. Now this is where I'm going to start bringing up some notation, because at this point here, I'm tired of having to write the magnitude of vector v. All right, so we're going to bring in some notation, and we're going to go back and use again one dimension here to help inspire us. And again, this idea of one dimension is going to come back in the last question for this thing here. So what did we use? If you think of this being, and let's actually put a dot here. So let's say this is our reference point. Okay, so we're measuring everything from that point there. Well, if I want to measure, say, the distance away from the reference point, okay, in other words, think of this being representative of where Broccoli Bear is, well, we could just use whatever number is represented on this number line. Well, ignore the phone ringing. Okay, Whereas if I'm on the other side, okay, the distance might be the same, except my position is on the other side. In other words, represented by some negative number. Well, what could I use to just represent the distance away from the origin? Well, of course, I use absolute value. Okay, so we talk about the absolute value of numbers, which is equivalent to the distance from the origin. So we're going to co-opt that notation in order to talk about magnitude. Okay, so here on the side, I'll write it out. So the magnitude of V is represented by two vertical bars around the vector. Okay, now this is where you have to understand that this is not the same as absolute value. Okay, so absolute value of 2. Okay, this represents absolute value, and this represents magnitude. So you might ask yourself, well, how am I going to know whether I'm finding the magnitude of a vector or the absolute value of a number? Well, it's all about context. If you see something with a little arrow around it, then we're talking about magnitude. If you see something that's around a scalar quantity, a number, then we're talking about absolute value. Okay, so if I want to talk about the magnitude of the vector kv, well, what did we say? It's k times, or absolute value of k times the magnitude of the original vector. So if I were to write this out using my notation, what's the absolute value of k times the magnitude of vector v? Okay, where in this situation here, these bars represent absolute value, and in this situation here, this represents the magnitude. Okay, so if I have the magnitude of the vector 3v, it's going to be equal to 3 times the magnitude of the vector v. So if vector v has a magnitude of 10, this is going to have a magnitude of 30. If I have the magnitude of vector negative 4v, okay, meaning a vector that's in the opposite direction of v but 4 times longer, well, let's see if our definition makes sense. Absolute value of negative 4 times the magnitude of v, which of course is 4 times the magnitude of v. In other words, same direction, but 4 times longer. Okay, so we're going to stop here and come back with a short little segment in part 3, but you might take a quick look at number 7 and see if you can figure out how we're going to do that.